Okay, there we go. Sorry guys, I almost forgot about you. You guys in the camera. So what we were doing is we were talking about a space sheet. We're over here, we're 2, 3, we're up f of 2, 3. So what's the coordinates of this point? I mean, let's at least get that. What's the coordinates? What's the x coordinate? 2. What's the y coordinate? 3. And what's the z coordinate? F of 2, 3. F of 2, 3. Now, what does the derivative represent in one dimension? What are some applications of the derivative in one dimension? I mean, how's that a useful tool? I know, Dr. Warren. Why are we learning about it? I mean, what does the derivative describe in one dimension?
Rate of change.
Rate of change. How f is changing, in this case, how f is changing with respect to... I'll help you. How f is changing with respect to x. How the range is changing with respect to the domain. And we know that, like, if this number ended up being 7, the function would be increasing or decreasing? Increasing at a rate of roughly 7, whatever the units of f are, divided by the units of x. Is that useful? Is that useful in engineering and physics and stuff like that? Okay, so it describes how quantities change. Do you think in most applications things are going to depend on more than one quantity? If you just had to guess, would you think it might depend on, think of the weather. Does that depend on more than just time? And so here we're saying that we only have 2 things. Now we're up here on this surface. As I move away from the surface, are things going to change? First of all, in one dimension, if we're in the domain, we're here at 2. We can either only go positive, or we can go back negative. But over here, we could go, how many different directions down here? How many different directions? Infinitely many. Now imagine this represents profit. Imagine this function represents profit at some point x, y. Would it be nice to know which direction to go in that would point us towards the most maximum profit moving away from that point? And these are some of the tools that we're trying to talk about. And the thing that's going to do that for us is the derivative. But we've got to ask, what the hell is the derivative in higher dimensions? So ask that. Well, you don't want to know. Okay? First, we have to have a definition of differentiability. Do we have a definition now of differentiability? And I've kind of written it down here. You guys help me out. I'm being lazy, differentiable at x equals a, but now a is just the vector 2, 3. If and only if there exists a d that's an element of our vector space. Now in this case, because my domain's only 2-dimensional, d's only going to have 2 components. We're going to have d1 and d2. What's a vector again? I hate you, Dr. Warren. What's a vector? An order triple of 3 real numbers. In this case, it would be an order double of 2 real numbers. If and only if there exists a d such that the limit as x approaches a. Now, because we can't have vector division, say that to somebody. We've got scalar multiplication, we've got cross products, and we also have dot products, but we don't have any division. So the idea of doing this with vectors is screwed. We can't say x minus a, dividing by x minus a. Does this make sense? And the reason is because of Gibbs. So let's say Gibbs, thanks a lot. Say that.
Thanks a lot.
We just taught us quaternions. I'm looking to work with Northrop Grumman a little bit on a project. And they store everything related to their aerospace quantities in terms of quaternions. So in the end, Hamilton won. It just took 100 years for it to be that way. I think Calc 3 will eventually be taught in quaternions. Not in terms of dot and cross products like we have right now. But we're not there. If it was quaternions, there is division, so we could talk about 1 over x minus a. But we can't here. So we have this butchered expression where instead of using x minus a, we're forced to use the norm of x minus a. Is that well defined? Is that well defined? 1 over the norm. Now, as x goes to 2, 3, where will the denominator go? When x goes to 2, 3, where will that norm go?
0.
0. So it is kind of capturing what we have. It is kind of capturing what we have. But it would be so much better if we just had the x minus a. Now ask me, what's the cost of having the norm?
What's the cost of having the norm?
We've got to have this absolute value. In order to reach anything, we've got to have the cost of this absolute value here is because of the norm. Now let's look at the numerator. The first thing in the numerator is f of x minus f of a, which looks really, really sweet from what we had over here. The problem is with the norm, we also have to have our derivative. Instead of having this be f prime of 2, instead of this being f prime of 2, what did I just say? What we do is we take the f prime of 2 to the other side, and we end up bringing it into the fraction. So we multiply top and bottom by x minus 2. And so this is what we've got kind of here. Instead of having the x minus a, we've got our d, but we're multiplying times x minus a, but x minus a is a vector, so our product has to be a vector product, not just, and we don't want it to be a scalar, because a scalar times a vector, this is a real number, this is a real number, units wouldn't match, And so we use our dot product. So if we look at this, the denominator is a scalar, that term is a, this term is a scalar, and when I do the dot product, this is also a scalar, and we say this limit has to go to 0. There has to exist a d, there has to exist a vector d, where this limit goes to 0. Is the derivative important? Just ask. Is the derivative important?
Yes.
Okay, would it be nice to be able to find the numbers d1 and d2? Would it be nice to find out what the numbers d1 and d2 are? Okay, what is the vector that actually is the derivative? Okay, so this is where we start. As you get ready for the quest, if the limit goes to L, if the limit as x approaches a goes to L, not C, the limit as x approaches a goes to L, then the limit along every what must also go to L?
Domain curve.
Domain curve, very good, Gordon. If this limit goes to 0, then the limit of along every other domain curve must also go to 0. Okay, so stand up. We're going to pick a very, look at somebody and say, wake up. Okay, Luke Marcus, I'm calling you, wake up. Robert Coleman, wake up. Brandon Landis, you better not be drinking a beer. Wake up. Hunter, good, see you there, okay. Brandon, are you there? Brandon? Okay, good, I see that. Luke's got the hand. I don't know how you do any of that stuff. Ava, are you there? Okay, Ava's not there. Ava. I know, my daughter's taught me. I know. Oh yeah, there she is. Okay, good. Raylan, are you there?
Yes, I'm here.
Okay. Grab your magic lasso. You're gonna want this magic lasso. Grab your magic lasso. Throw your magic lasso. Rachel, throw that lasso. Okay, now what are you wrapping up, guys? What are you wrapping up? You guys are gonna need your attention span more than ever before. Okay, sit back down. Okay, I'm going to pick a domain curve, but it's going to be a very specific domain curve. If it's a domain curve, it's got to go through A. Well, who's A? 2, 3. I'm going to pick the line. That runs through 2, 3, but is parallel to the x-axis. I'm going to pick a line that runs through 2, 3, but sits parallel to the x-axis. So draw that line in your drawing. Draw the domain curve down there in your drawing. Now I totally failed my students in my first class. So I did this. How many people got that? How many people got that? Then I had the nerve to say, I say line, you say A plus TD. You know, and they're like, okay, so I need a position vector and I need a direction vector. And I'm not going to pick the position vector you think I'm going to pick. I'm not going to pick the position vector. I'm not going to pick the one that would run to there and position to the point. It works out a little easier if I choose this vector right there to be my position vector. Now, what is that vector? Let's think about what that, my A, which can't be this A. See, I'm running out of letters again, guys. I'm running out of letters. If I think about what the vector would be for the line, what vector is it? How far am I in the x direction? How far am I going in the x direction?
0.
0. How far am I going in the y direction?
3.
3. So my position vector would be 0, 3, plus t, and then I said d. And I'm thinking, okay, what's the simplest direction vector that I could pick that would point in this direction? You know, and I'm like, well, how about the vector I? Doesn't that point in that direction? And what are the coordinates of I? 1, 0, 0, but now I'm in plane, so we can just use 1, 0. And this is where I failed. Because I said line, I say line, you say A plus TD. And then we found out D1. We found out D1 was written in terms of a limit. And one poor kid was like, wait, Dr. Warren, D is 1, 0. And I'm like, oh, what the hell? Seriously, you guys, oh, no, 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 no. This is the direction vector for the line. This is the derivative. So to save me, how many people recognize the difference? How many people recognize the difference? So if I'm thinking about this, my space curve, my domain curve down here, my R of t would just be, well, you guys help me out. Do this scalar multiplication and vector addition. And what do you get? What's the first component of my domain curve? T. Very good, Rhett. What's the second component? What's the second component of my domain curve? 3. Now, if I'm a domain curve, I also need a value c. I also need a value c such that R of c actually hits the point 2, 3. I need a c such that R of c actually equals the point 2, 3. And what's would the c be, guys, for this domain curve? 2. So my c here is 2, and you can just plug 2 in. You clearly see that it's 2, 3. How many people think they may be running limits along domain curves on Friday? You're just wondering. How many people have actually started the homework in 14? If you haven't started the homework in 14.2, I'm so sorry. I'm so sorry. I failed you. You should have been working on the homework in 14.2. Is that on the quest? Is that on the quest? When's your quest? Friday. Are you asked to run limits along domain curves in there to answer some of the questions? Yes. Yes. Okay, so you guys help me out. If the limit is equal to 0, then the limit along every domain curve must also be equal to 0. How many people realize Dr. Warren's not writing this whole damn thing down again? How many people realize I'm not going to write that all down again? Okay, so I'm going to just say I'm going to run it along the domain curve. I guess let's call it C. This is going to be my domain curve C. Here's my domain curve. So I'm running this limit as x approaches A, which is 2, 3. And then I'm just putting quotes, air quotes here, and we're all pretending like Dr. Warren wrote all that crap down all over again. You will have to do this on a quest, not all of this. But on Friday, if you run it along a domain curve of a function like x squared plus y squared, you're going to have to write the x squared plus y squared there. I'm just not doing that. And then I would put a what down here? I would put what down? C. Now we're going to start. Well, that would be the same thing as, and this is a step you would need on Friday. the limit as what? And we'll see what's in your gray mat, or what do you do next? It's the same thing as the limit as what if you're running it along a domain curve. This is the most important step right here.
T approaches 2.
Limit as t approaches 2. I know. Who said that? Who said that? Who said that? Who said that?
No, it's me.
Gordon. Good, Gordon. Thanks. Okay. Now you guys help me out. Wherever I see an x, I'm going to put a t. Wherever I'd see the y, I'm going to put a 3. But my vector x is xy. So if I just start doing that, let's start on the bottom. Let's start on the bottom. I would have the norm of the vector x, but that's like xy. But x is who on this domain curve? X is who? T. Y is who? Y is who? 3, always just 3. Minus 2, 3. Okay, let's start up here at the top. That minus I just drew is this minus. I would have D dotted with xy, but now again we're on the domain curve, and x would be t and y would be 3, so that I'd have. You guys help me out. What would go here? What would go there? What would go there?
2.
2. What goes here?
3.
What goes there?
T.
T. What goes here? 3. Now let's finish this numerator. There's nothing to change. This is just f of 2, 3. Something's going to change over here. I've got f of x, but my x component was t, and my y component is 3. I know no matter what I say, nobody's going to. What do? Oh, okay. This is me wearing last night's election. Okay, this is me wearing the election right here. This is what I feel like. Okay, it's on me. Now, again, why are you doing this, Dr. Warren? Because I know you won't listen. No matter what I said at that moment, it was just going to go right in one ear and out the other. How many people got here to see and why the definition of differentiability is what it is? How many people kind of get the definition of differentiability in this class? Do you get why we can't have division down there? Do you get why we need the norm? And that screws everything else up because we need the absolute value. Do we have the f of x minus f of a? Is it actually in? Is it in the definition there? We expect the derivative in higher dimensions to have more components. We would expect that. Maybe you wouldn't, but it makes sense once I write it down. This limit goes to
0.
If the derivative exists, the limit goes to 0. Then the limit along every domain curve must also go to 0. Is this a legit domain curve? It's a simple one, but is it a legit domain curve? And so we're just using, let me take off the election. Last I saw, Biden was up in Michigan. We'll see. Guys, I survived oh my gosh. I survived Bush Gore, okay? Which we had to wait weeks and weeks and had to go to a Supreme Court case. How old were you in 2000? How old were you in 2000? How old were you guys? I mean, like in 2000. Were you negative numbers or how old? 1?
Negative.
You were negative. Okay, so yeah, for you that's history, right? For you that's history. Guys, I mean, I know it always seems like it's such a big deal, and it is a big deal. But guys, in general, it's all going to be okay. Look at me. And no matter what, it's in the end all going to be okay. Because it's not them, it's you. You're the future. You're the future. Look at somebody and say that. Hands on the space bar. Hands on the space bar. Say that. Say that. Say that. Say that. Hands on the space bar. Say that. You're the future. And you guys have all kinds of potential. I see it every day. The future is yours, and it's a good future. You do struggle with commitment. I have to say that. You do struggle showing up on time. I found that I have to tell my students the day of. If we have a meeting and I don't remind them the day of, they may not show up. I'm like, what, did you not see that? Well, yeah, but you didn't send me a reminder. I'm like, what the hell? What do you mean I didn't send you a reminder? Wait, Dr. Warren, you should really send something about 30 minutes or people won't show. I'm like, what? And I don't quite get the whole not flushing the toilet stuff. My generation, flush the toilet. But they also flush the toilet on the entire country. So, so let's just, sorry. Yeah, I know. It is, like somebody was saying, well, if it's yellow, let it mellow. And I'm like, what the hell are you talking about? And they're like, well, Doc, you don't want to waste water. And I'm like, we're not flushing toilets because we're wasting water? And she's like, if it's yellow, let it mellow. If it's brown, flush it down. And I'm like, oh, I get it now. It's a urinal. It's a urinal. If it's brown, run, run, run. Sorry. Okay. And that's the way the country is right now. Okay, sorry. I'm sorry. I'm sorry what my generation has done. Global warming. Okay, enough. The limit along every, you needed a break. The limit along every domain curve must also go to 0. Is this a legitimate domain curve? Is this a legitimate domain curve?
Yeah.
Then this limit must also go to, and it's really important, must also go to 0. Okay, now you guys are going to work instead of Dr. Warren working. How many people know how to take vector subtraction? How many people know how to take vector subtraction? Have I taught you well enough to do that? How many people know how to take dot products? How many people know how to take dot products? So what I want you to do, don't worry about these two terms. Don't worry about these two terms. But I want you to simplify. I want you to simplify the denominator and simplify that as much as you can. Instead of you guys just scribing what I write down, you guys write down.
Dr. Warren, Luke had a question in the chat, but his mic doesn't work.
Oh, Luke, what was your question, man? Oh, sorry, your mic doesn't work.
I'm going to say it for him because he doesn't have a mic. So he said since the f of x in the first equation has a vector x, does that mean there should be vector brackets inside the f of x, or do we drop the bracket?
That's a great question, Luke. We almost go interchangeable with that. So it probably shouldn't be. You keep it like this, but that's a great question. The vector notation is just kind of comfortable, but it's a great question. And I'm sure you weren't the only one. For sake of time, what do you guys have for the denominator? What does the denominator simplify to once you're talking about the norm and everything like that? What do you get? What do you get when you do the subtraction here? What vector do you get doing the vector subtraction? T minus 2, and then what's the other component? 0. Now, how do you take the norm of a vector again? Square it and add them together. But what's 0 squared? 0. So this would simplify down to, the square root of what? This would simplify down to the square root of what? T minus 2 squared. Did anybody have that? Now let's look up at the other part here. Let's look up the numerator. Again, if I do that same subtraction, I get t minus 2, 0. How do you take the dot product again? Well, if it's d1, d2, it would be d1 times t minus 2 and d2 times 0. So when you add those together, who's going to go away? The second component. So we'd only be left with minus d1 times t minus 2. And again, this limit's got to go to what? Since we're running along this curve and the limit exists, this also has to go to 0. How many people are following? How many people have kind of followed so far? Okay, what's the square root of apple squared the same thing as? What's the square root of apple squared the same thing?
Absolute value of apple.
Absolute value of apple. The absolute value of apple. So this would be the same thing as the absolute value of t minus 2. Do you agree or disagree? So I'm going to keep the notation down. I'm going to keep the writing down. But if you have the absolute value of A over the absolute value of B, is that the same thing as the absolute value of A over B? You don't even need to write this down. Is the absolute value of A divided by the absolute value of B the same thing as absolute value of A over B? So this is like the absolute value of t minus 2. Could I bring it inside the absolute value that's upstairs? Could I bring it inside the absolute value that's upstairs? Now, it would come in as a t minus 2, but look over here, we have a t minus 2. So that suggests breaking this into 2 fractions. If you have 2 plus 7 over 3, Dr. Warren, this is the easiest stuff we've done all semester. I know the answer, it's 3, that's not the point. Okay. 2 plus 7 over 3, is that the same thing as 2 over 3 plus 7 over 3? So let's imagine that I've taken this absolute value inside, and I take it to this term, and I take it to that term. What happens when I take it to that term? What happens when I take the absolute value of t minus 2? When I bring it in, it's going to come in as a t minus 2. What happens there? It cancels, but it stays with this one. So keeping the notation down, and I guess I really don't have any other place to go but up here. So this would imply, just using some properties of absolute value, I still have my limit here. T is going to 2. I've got an absolute value. If the result is still 0, except now I've got a minus, and I don't even have a fraction in the second one. What's the only thing left over there on this other term? What's the only thing left on the other term? D1. And since I've taken this absolute value in, what's the fraction? What's the fraction over there? You would have, well, what would the denominator be? What would the denominator be?
T minus 2.
T minus 2. And what's the numerator? What's the numerator? F of t3 minus f of 2, 3. Okay, stand up. Wherever you're at, stand up. I know you need this. You know you need this. You know you need this. Stand up, stand up. Stretch, stretch. Okay, let's sit back down. Let's think about our adventure today. Dr. Warren, I've been hating the adventure. Let's think of it. This is our definition of differentiability. How many of you are glad we're using a 2 and a 3 and not an A1 and A2? I mean, if you had to ask. How many of you are like pretty happy we're using 2s and 3s? Okay, so here's my domain point A. Is this a legitimate domain curve? Is this a legitimate domain curve? Yes. It's a line. Is that the same thing as that line? Is that the same thing as that line? What's the C value that hits the point? What's the C value that hits the point? 2. If I run this and this equals 0, then the limit along that domain curve must also go to 0. So I'm just plugged in, just like you'll do on Friday, but not to this ugly thing. Something much simpler. Wherever I see the x, wherever I see an x, I'm running along the curve, I put a, wherever I see the y, I'm putting a
3.
Does it make sense that we would go here? Does it make sense that it would go here? Then how many people are pretty comfortable like moving into this point? How many people are pretty comfortable moving into that point? This is the hardest thing. The square root of this is the same thing as, the square root of this squared is the same thing as the absolute value. I take the absolute value, I take it inside the absolute value. I break this into 2 fractions. How many people will follow it? How many people are kind of following where we're at right now? Okay, this is where the absolute value becomes a pain. But it's okay. The limit of this absolute value mess is going to 0. But if the limit of the absolute value of a function goes to 0, then the limit of the functions, one of our theorems, if the limit of the absolute value of a function goes to 0, then the limit of the function must also go to 0. So the limit of this thing with respect to t must also go to 0. But that guy's a constant. He's a constant. He's a constant. He's the first component in my derivative vector. You're a vector if you're a, I hate you, Dr. Warren, order triple of 3 real numbers. In this case, you're an order double of 2 real numbers. What's the limit of a constant? And if you say 0, I'm going to vomit. What's the limit, not derivative? What's the limit of a constant? The constant. So the limit as t approaches 2 of d1 would just be d1, and this limit has to go to 0. And so we end up with this. The d1 that we're looking for, the first component in my derivative, is defined in terms of this limit right here. It's the limit as t approaches 2. Now look who's in the bottom. Look who's in the bottom. Look who's in the bottom. Who's in the bottom?
T minus 2.
T minus 2. And on the top, I've got f of t 3 minus f of 2, 3. And that limit represents the first component in my derivative. And you're like, hey, Dr. Warren, that's not that surprising. Look, Dr. Warren, the first component of the derivative is defined in terms of a limit. Oh. And as t goes to 2, the denominator goes to
0.
And as t goes to 2, the numerator goes to
0.
In fact, Dr. Warren, it looks a lot like f of x minus, it looks like a lot like f of x minus f of c, all divided by x minus c, except for the stupid 3. I mean, doesn't it kind of look like that? It looks just like a derivative. Doesn't it look just like a derivative? With the exception of the 3. But here's the thing, guys. 3 is like a constant. So it's exactly like taking a derivative. But we can't call it taking a derivative. So we say this is a, now get it. D1 is part of the derivative. Say that.
D1 is part of the derivative.
D1 is part of the derivative. We call this the partial derivative of f. Now, which variable's changing, the x or the y, and which one's a constant? Which one's changing and which one's a constant? The x is changing. So this is the partial derivative of f with respect to x at 2, 3. At 2, 3. And this is a flashcard. This is a flashcard. But I'm going to write it down now as a flashcard that I want you guys to have. I guess I got to get rid of all this. How many people realize this notation is screwed? How many people are like, if we have an x and a y, can prime work? Can prime work for derivative? Can prime work? Because you're like, do you mean x or do you mean y? So there's this other notation, the Leibniz notation, which is df by dx. Do you remember that? Do you remember that, df by dx? So there's a similar notation that we call partial derivative notation, which uses something that looks like a d, but it kind of swings around. It's a partial sign. It's the partial derivative of f with respect to x. And then if you had to guess, what do you think the symbol for the partial derivative of f with respect to y would look like? If you just had to guess, what do you think the partial derivative of f with respect to y would look like? Partial f divided by
Partial y.
But Leibniz's notation is kind of annoying because you have to draw this x equals c. And so we would have to have here xy equals 2, 3. And we don't want that. So we get lazy. Instead of using a prime, we use a subscript. Instead of using a prime, we use a subscript. And I'm not sure when this notation came around. I think it was maybe in the 1800s. I think this was around in the 1700s. But this came around, I think, in the 1800s. And so we say this is the partial derivative, say this. Partial derivative of f with respect to x of the function x that depends on xy. And then what do you think? Write down what you think. Take a wild guess at what you think the partial derivative of f with respect to y would be. Just the symbol that we would use for this. Some people aren't writing anything. What do you guys think? What do you think it would be? If you had to guess, what do you think it would be? F, and then what do you do? Then what do you do? Little subscript, and then you've got a xy. Okay, here's your flashcard. Here's your flashcard. F of x, and I know at home you guys might be able to see that. Let me just get rid of this. Is that better, guys? Is that better at home? Is that better there? So read this. Read this. Read this. Read this. No one. Read this. Partial derivative of f
With respect to
x at 2, 3 is defined to be this. It's the limit as x approaches, 2 of f of x 3 minus f of 2, 3 divided by x minus 2. No, it's got to be.
No, my phone's doing.
Oh, no. Okay, good. I'm sure it's me all the time. Do you guys see this anywhere else in the room? Do you guys see anything that looks like this anywhere else in the room? Look at this limit. Do you see this room anywhere else in the room? Do you see this anywhere else in the room? You're like, hey, Dr. Warren, that's just like your D1. So this is D1. This is D1. We're not going to use T. Okay. What time is class in? Look at your watch, look at anything tells time, and just think, oh, you gotta be kidding me, there's still that much time left. That's what you're thinking at home. You guys thinking, Hunter, yeah. How are you doing, Hunter?
I'm doing good.
Okay. Hunter, are you following this at all?
Yes, sir. I am. It's a
little much.
little bit confusing, but the more you talk about it, I feel like the more I understand it. Instead of just like writing it down, I like that you take the time to kind of like explain it, and that definitely helps.
Thanks, Hunter. It's kind of like painting over mildew, isn't it? You know, you keep painting and the mildew seeps something through. You keep painting and more mildew. Okay. Let's take one more. Let's take a recap. This is my definition of differentiability in higher dimension. D is my derivative. D is like my derivative. It has two components, D1 and D2. We just argued that the D1 is the partial derivative of f with respect to x at the domain point 2, 3. You're like, how do you calculate that, Dr. Warren? Well, sadly, it's defined in terms of a limit. Okay, let's do this all over again. You're like, Dr. Warren, not a chance in hell. There's not a chance in hell you're going to do this to me again. Okay, I agree. I'm not going to do this to you again. He cut to me. Why didn't I turn that off? I hate these things. I lived without this. I lived without this for 20 years. I never had one until a year ago. Alzheimer's did this too, not mine. I'm sorry. Okay, sorry. What are you doing, Dr. Warren? I'm just trying to keep you awake. That's why I had that phone go off. I didn't, but I had Cameron's phone go off too. You didn't know I had that power. If I did this curve, if I ran a curve that was parallel to the y-axis instead of the x-axis, would it still be a domain curve? Would it still be a domain curve? If instead instead of using t3, if I used 2t, would that be cool? Would that be cool? Then the c wouldn't be 2, the c would be 3. And I could run through the whole game that I just did. Over, plug it in, take the norm. Now instead of the first component, the second component going away, the first component would go away. And instead of a t minus 2, I would have the square root of t minus 3 squared. And I could keep moving, and I could keep moving up here, instead of the y component dropping out, the x component would drop out. I would have a t minus 3 up here, just like what we had with our t minus 2. We'd still have the absolute value. We could still bring it inside. And lo and behold, when the smoke would clear, we could show that d2 would be equal to the limit, not as t approaches 2, but the limit as t approaches 3. And on the bottom, we wouldn't have t minus 2, but we would have t minus 3. Now it gets a little more confusing on the top. Not. It's still f of 2, 3. It's still f of 2, 3. It's just we don't have f of t 3. We would have f of, can anybody guess? 2t. And we call this the partial derivative of f with respect to y at 2, 3. In our flashcards, we don't use the t. Now, instead of having the limit as t approaches 3, we have the limit as, can you guess? Can you guess? The limit as y approaches 3. And on the bottom, what do you think we're going to have down there? On the bottom, what do you think we're going to have down there? Y minus 3. And on the top, we're going to have a f of not x3, but f2y minus f of 2, 3. And these are my partial derivative flashcards. These are my partial derivative flashcards. These will replace 108 and 109. These will replace 108 and 109. I already did it. I already put up a new file on Canvas for you. Whew! Hallelujah, we're there. Okay. Now stand up again. It's just one of those days. It's just one of those days. And Friday's worse because you have a, and you get back a. Yeah, okay. Stretch. Okay, sit back down, sit back down. Who's the future? Who's the future? Who's the future? Who's the future? You're the future. You're the future. You're the future. I say that to my daughter, and she's like, well, Dad, I don't know if I'd put a lot of hope in us. I'm like, you're all I've got, sweetie. You're all I've got. You're the future. You know, the thing is, guys, I love my job so much. I would do this for free. I would never tell any of my dean that or my department head, but I would do this for free because it's just so fun. It's so fun. It's so beautiful how it all works together and how it's all solid. And not only that, I get to work with you guys. I get to work with your young minds. Hopefully not disturb them or pollute them too much. But I get to work with your minds. And you guys, I mean, I love JMU kids. I really always have loved JMU kids. I went to UVA for grad school, and I had to deal with those students, and they're just not the same. There's just an air over there that annoyed me from the very beginning. There was this country club air, and I just couldn't quite take it. I mean, I was just like, I just kind of felt dirty, you know, like this entitled kind of thing. You know, where here you don't get any of that. You don't get entitled. You get kids that hide how smart they are here. They don't really want to show how smart they are. Over there, everybody's trying to show how smart they are. And I'm like, no, you're a moron. I mean, I'm an idiot, okay? I have 1.9 as grade on average, but no, you cannot distribute sine. Why can't I? I did it back in high school. I'm like, well, because your teacher taught you wrong. I'm sorry, sine of A plus B doesn't equal sine of A plus a sine of B. Why not? And I'm like, holy hell, kid. You know, I mean, seriously? Let's just move on with you wrong and I'm right so that we can't do this. And he's like, I don't believe you. So then we had to do some numbers. And then eventually 5 minutes later, I'm right, he's wrong, but he's wasted all this time. And then when I start talking about other things, he can't remember. I never had that one time here. Not one time. Had kids come in, Dr. Warner, I got a bad grade on this. Why did you take off that? That's fine, I understand that. But I can't understand like something I'm telling you, you're wrong. Like, no, I'm right. Also, like here, like, I don't know, there's just a community spirit that I've always loved. There's a community spirit. I've always believed we play hard, we work hard at JMU. I've always believed that. Play hard, work hard. And I think that's kind of the mentality that runs around. Play hard. Yeah, no, it wasn't play hard. It was play hard, work hard. Right now we are working hard. Okay. So back to where we were. Okay. Dr. Warren, how do I actually calculate these things? So ask that.
How do you actually calculate that?
Do you seriously expect me to do it in terms of a limit? Ask me that. And you're really hoping the answer is no. No. And the answer is, in fact, no. Okay. It's defined in terms of a limit. But in application, it's not as bad as it seems. Because if I look at the first one, the partial derivative of f with respect to x, look, the only thing that's moving is the x. The y is always fixed at 3. And vice versa, when I'm looking at the partial derivative of f with respect to y, the only thing that's moving is the y. The x is fixed at 2. So this is a dirty trick. When you're taking partial derivatives with respect to x, you can think of y as being a constant. And when you take the partial derivatives of f with respect to y, you can think of x as being a constant. Partial derivative of f with respect to x, You can think of y as being a, we'll keep going, constant. Partial derivative of f with respect to y, you can think of x as being a constant. So give me a space sheet. I'm always afraid every time I say sheet. I'm always like, after messing up that one time, give me a space sheet. I need a function of x and y. I need a function of x and y. Okay, it's not hard. This is maybe the easiest question. This will not be on the quest, okay? Give me a function of x and y. No, that's not going to ask that. I'll give you function. But give me a function of x and y. Anything, anything, anything.
X squared, y squared.
X squared, y squared. Legit space sheet, legit space sheet, legit space sheet. Now imagine I wanted to calculate, imagine that I wanted to calculate f of x at 2, 3. Imagine that I wanted to calculate this. Let's first of all calculate it for any x and y. Before we're calculating it at 2, 3, let's calculate it for any x and y. Now, am I taking my partial derivative with respect to x? I almost took the camera out. Partial derivative with respect to x or partial derivative with respect to y? X. So I can think of y as being a constant. Now imagine y squared was 7. I know you can't. But imagine y squared is 7. What would the derivative of x squared times 7 be? You can do this. I know you can. What is the derivative of x squared times 7? You're in Calc 3. 14x. How many people got that? How many people got that? 14x. How many people got it? Okay, so now imagine that it's 12. What's the derivative of x squared times 12? 24x. Dr. Warren, this is easy. What if it's y squared is the constant? Dr. Warren, I can't do that. Yes, you can. It's the same thing. It would be 2x times y squared. We're thinking of that as being a constant. So my partial derivative with respect to x would be 2x, thinking of y squared as being a constant. Then how about the partial derivative of f of x with respect to y? You guys take a shot at that. You guys take a shot at that. What do you think the partial derivative of Michael's space sheet, x squared, y squared, with respect to y would be? 2x squared y. Now I want these at 2 and 3. So that's not that hard. Wherever I see an x, I'm going to put a 2. So it'd be 2 times 2 times 3 squared. Now you guys can help me out. 4 times 9, 4 times 9, 4 times 9, 4 times 9. 36. Fy at 2, 3 would be 2 times 2 squared times 3, which is 8 times 3, which is 24. So what's your derivative? What's your derivative? What's your derivative? What's your derivative?
36, 24.
36, 24. Is that a legitimate vector? Is that a legitimate vector? Yes, and so there's my derivative vector. So in general, the D ends up being, let me get rid of this. The first component is the partial derivative with respect to x at 2, 3. The second component in your vector is the of f with respect to y at 2, 3. Okay. How many people are glad this isn't on the quest? How many people are glad this isn't on the quest this week? I know you guys at home have no idea what we're doing here. I will. All right, can you guys see that at home now? Can you guys see that at home? Can you guys see that? So I want you to look, this is the exercises in 14.3. This is the exercises in 14.3. So let's just look at that for a second. This says in problems, I love this. I don't think I've ever seen this in a calc book. In problems, it usually says like 15 to 20, but this says 15 to 40. In 15 through 40, calculate the first partials. Okay, and so what that's asking is find the partial derivative with respect to x and find the partial derivative with respect to y. So let's look at this first one. Let's look at problem 15. If you're taking the partial derivative with respect to x, who's like a constant? Y. So if I was taking that partial with respect to x, what would you get there? 4x cubed. Now remember, y cubed is like a constant, and so what would you get with that term? Plus 5y cubed. Let's see how we did. Did you guys say 4x cubed plus 5y cubed? Now let's take our partial with respect to y. Let's take our partial with respect to y. Now x is like a constant. What's the derivative of a constant? What's the derivative of a constant? Not the limit. What's the derivative of a constant? 0. So this is 0. Now I'm thinking of this, again, x is like a constant. So ignore the 5x. What's the derivative of y cubed?
3y squared.
3y squared. So this would be like 5x times 3y squared, which is our 15xy squared. Does that make sense? Does that make sense? Okay, so now I want you guys to do, make it xy. Write this down, and at home do the same thing. Write down f of xy, equals y squared times e to the minus x. And calculate those partials, You know this is the bulk of the assignment if it's 15 through 40. Now I'm hoping on a quest you guys would be done. Now I've got to ask, if I'm looking at this, do I have to use product rule? Do you have to use product rule? And the answer is no. Because here we're thinking of y as being a constant. So now, let's not mess this up. What's the derivative of e to the minus x? Negative e to the minus x. So my partial should be negative, now help me out, negative y squared e to the minus x. And what's the second one? What's the second partial? What's your partial with respect to y? 2y e to the minus x. 2y e to the minus x. Oh, that's right, I didn't stop sharing. You poor guys at home. You're seeing it in that little tiny window. I'm so sorry. There's lots of empty seats here. There's lots of, okay, so let's check. Let's see what we got. What's their answer? What's their answer? What do they have? They've got e minus t squared, but t is y. E to the, is that what we got? Is that what we got? And then here, did we get 2y e to the minus x? Is that what we got?
Yep.
Is this making sense? Is this making sense?
Yes.
Okay, so now you guys try problem 19. You guys try problem 19. And again, you can change t to y. You can change t to y. It's stupid that they have that as t. Because t is their parameter for space curves. So you got the natural log of x plus y squared. See how many people mess this up. Let's go back. How many people know how to take the derivative of that? How many people know how to take the derivative of that? What's the derivative of that? What's the derivative of that? What is the derivative of that? 1 over f of x times f prime of x. How many people know that flashcard? How many people remember that flashcard? So who's kind of like playing the role of the f of, I mean, think about f of x, y. I've got my x plus y squared. So if I take the partial, with respect to x, it's going to be, I hit my natural log, it's going to be 1 over x plus y squared. Now we take our partial. What's the derivative, partial derivative of x plus y squared with respect to x? 1. Because the derivative of this would be 0. So I just get 1, and so this would be my partial derivative. Now let's do the second partial with respect to y. Well, again it's going to be 1 over x squared plus y, x plus y squared. But now, what's the partial derivative of the inside with respect to y? Well, that's 0, and this would be a 2y. This would be a 2y. And so let's go back and share and then see if we did it, see if we got that right. Okay, so we're here, now their t is y, so let's see what we did. What did we get for our first one? What did we get for our first one? We got x plus y squared. Is that what they got? Is that what they got? And then they got 2t plus over x plus t squared. But isn't that the same thing that we got? Isn't that the same thing that we got? Okay. So let's finish class with this one. Let's finish class with this one. Take the partial derivatives of the function x over y. For sake of time, I'm just going to share the answer. For the sake of time, I'm just going to share the answer. Did anybody get anything for fx? Did anybody get anything for the partial derivative of f with respect to x? What did you guys get?
1 over y.
1 over y. And what did they get? What did they get? 1 over y. Now let's look at the second one. It ended up being what? What did they get for their second one? Negative x over, so write that down. Write down negative x over y squared. And let me just try to explain this. How many people understand this? How many understand the first one? How many people kind of get the first one? Okay, so now let's look at the second one. You can either rewrite this as y to the negative 1 and go at it with power rule, but let's say you forget this. Let's use quotient rule. It would be the partial derivative of the numerator with respect to y, which would be x doesn't depend on y, so the partial derivative of the numerator with respect to y would be 0 times the denominator minus the numerator times the derivative of the denominator with respect to y. But what's the partial of the y with respect to y? 1. And then in quotient rule, what goes on the bottom? In quotient rule, what goes on the bottom? Bottom squared. Do you see how we end up with the same thing? Do you see how we end up with the same thing they got? This term dies, and then we're left with minus x over y squared. Okay, I assign only about, I think, 20 of these problems.